continue talking about it today. Probably wrap it up a little bit tomorrow. Again, if that's in anybody, if the camera's in anybody's way, go ahead and feel free to move around a little bit. Find your desk, left or right, whatever. Alright, so we talked. I don't think you guys got to this situation on Friday before our quiz, and I'll get those back to you as soon as possible. But this thing here, quadratic formula, okay? Something you guys are familiar with, correct? Yeah. Alright. What I want you guys to realize, and we're going to go through the algebra of creating this real quick, but what I want you to realize is this is nothing other than completing the square. Okay? It's just that completing the square is a very time-consuming procedure if I've got to do it 3, 4, 5 different problems in a row. Okay? So we've recognized, okay, that we're doing the same thing over and over again. So why do we care what our coefficients are? Let's just make them arbitrary, A, B, and C, and do the exact same procedure of completing the square with A, B, and C. That should develop something for us that we can now use as a shortcut every time we get a quadratic equation that allows us to complete the square much faster. Okay, so here's the idea, here's the logic behind it. Now you've seen this before. There's a video on my website that goes through this as well, if you want to look at that. But just so that we're all on kind of the same page here, and we've all seen it at least once, I do want to go over it. Alright, so completing the square. When your first two steps of completing the square are independent steps. It does not matter the order that you do them. Okay? But you have to make your A coefficient a 1. Okay? So how can I go through and make that a 1? If I've got an equation and I want a coefficient to become 1, I have to use what operation? Division. Okay? I have to divide by itself, right? That'll give me a 1, correct? I can't just divide the A by itself. I have to do that to what? Everything. Okay? Can I divide 0 by a number? 0 divided by 5 is okay, right? That's still 0. Okay? So we're going to divide 0 by A, so there's no problem with that. The second thing is to move your constant term, which in this case is the non-variable term, so it's this one here. You have to move that to the other side. Okay? So you can do those two steps how you want to do it. Either move the C first, or divide out the A first, and then move the C. I like to do them both at the same time. So I'm going to go x squared plus b over a x equals the opposite of c over a. Does that kind of make sense? If you were to do it in two steps, you would have a line there that says maybe ax squared plus bx equals the opposite of c. And then you would go through and you would divide everything by a, and that's what you would end up with. And that allows you, that gets you in the arrangement to where you can complete the square now. Okay, what's the first step other than those two things? So it's the first numerical part of completing the square. What do we always do with this term here? Cut it in half. Okay, cut it in half, divide by 2, multiply by a half. Right? Those are all the same thing. Multiplying by a half is, at least here, the easiest thing for us to do. So we're going to multiply by 1/2. And then what do you do? Square. Okay? So I'm going to multiply this by a half. And I'm just going to do this work down here, and I'll erase it. But I'm going to multiply it by 1/2 would look like that, correct? Okay. Some people say divide by 2. If I divide by 2, it's a little bit longer of a process. B over A divided by 2 is the same as that, right? To do that division, don't I have to do that? Take the reciprocal of the bottom, multiply by the top. Does that give me B over 2A? Alright. So we're taking half of that middle term, and then you guys said square, right? That's what I said. So I'm going to square this. Well, when I square a fraction, I square the top, square the numerator. Okay? Square the bottom. So it becomes 4. You square the 2, right? And you square the A. So I get that. And that's what gets added to the left-hand side. What do I do to the right-hand side? If I added this to the left, what do I need to do? Add it to the right. Okay? Now completing the square, if you think about it, the reason we complete the square is because it creates that side, the left-hand side, it creates it as a perfect trinomial. Which means it can be written this way. Square root of that number, or term, and then whatever that symbol is here, and we're assuming that all these things, whether A, B, and C are positive or negative, we don't really care. We should keep them as plus signs. Because B could be negative, so it could be plus and negative 2 or something like that, which would be ax squared minus 2x. But we don't really care whether A or B is positive. We're going to keep that, or negative, we're going to keep that as a plus sign. So that goes right there. Whenever you complete the square, whatever that symbol is what that one ends up being. Okay. And now this term is your middle term divided by 2. It was that b over 2a term. And then we'll square that. Okay. Just real quick, if you wanted to, you don't need to, but if you wanted to, you could FOIL this out. X squared will give me x squared. Okay. Multiply these two things together, so I get bx over 2a, right? We'll double that. Okay. You'll have 2bx over 2a. Well, 2's are going to cancel out, right? So let's just get bx over a, which is that middle term. And then if you square the last term, you get that. So I do know, working my way backwards, that this on the left-hand side here is exactly the same as this on the left-hand side. Okay. I'm going to do a little bit of algebra here. I'm going to combine those, because I have two fractions, right? Let's make it one fraction. What's my common denominator I'm going to need to make that one fraction? Say again? 4a squared, right? They have to be the same denominator, correct? So multiply this by 4a, and that will give me 4a squared there, right? Come up here and multiply that by 4a, correct? So what that gives me up top, negative 4ac all over 4a squared, plus then b squared all over 4a squared, right? Is that doable? That's what I would get if I would have multiplied all that out. Now what do you recognize about these two denominators? Now they're the same, so can I combine the numerators? So I'm just going to write it this way. Plus sign there. Make that one long division bar. And make that 4a squared. So that's what that right-hand side condenses down to in one fraction. Okay. Now the goal, whenever we factor something, whenever we solve a quadratic equation, we're trying to solve for what variable? X. Okay? So if I'm trying to solve for x here, how do I isolate x? How do I get that by itself? What's the operation here that's inhibiting me from working inside those parentheses? Yeah, the power of 2, right? So I've got to square root things so I can do that, correct? Come over here and square it. So on the left-hand side, that's real easy. It's going to leave me an x plus b over 2a, right? On the right-hand side, there's some stuff in there I'm going to just kind of rearrange. The first thing I'm going to do is recognize that this is a fraction, right? If you have a fraction underneath a radical, our laws of exponents, and we'll get into this in a little more detail later, but our laws basically tell us that you can write the top as a radical and the bottom as a radical. Okay? We remember doing that, right? Okay? I'm going to take the top and I'm just going to rewrite it this way. I'm going to put the b squared first and the 4ac second. Does that start to look familiar? And just using the commutative property there to move things around. Now the bottom, what kind of number is 4a squared? It's a perfect square. What's the square root of 4? 2. What's the square root of a squared? A. Now that thing's starting to look pretty familiar, right? Solving for x still. I'm going to subtract this quantity over there. Okay? Something I forgot here. When we take the square root of a number, how many solutions do you get? You get 2, right? So that's why this is plus or minus. Okay. Now you have two fractions here, right? But what do you recognize about those two fractions? Yeah, they have a common denominator. So let's just do this. And we've developed then the quadratic equation, right? Or sorry, quadratic formula from a quadratic equation. Okay? And what that tells us now is regardless of what, because we didn't care what A, B, and C were. We didn't care if they were positive numbers, if they were negative numbers. Really the only thing we care about is A cannot be 0. Okay? Because if it's 0, then that becomes a linear equation. It's really easy to solve it. So that's really the only requirement is that A cannot be 0. We should be able to plug whatever the B coefficient is, whatever the C coefficient, the A coefficient are, plug that into there, and it will automatically do all the work that completing the square did. Because that factoring, the quadratic formula, is exactly the same as completing the square. Does that make sense to everybody? All right. And that's just what I want to make sure you guys understand, is that the formulas that we come up with in this class, and we come up with in physics, and come up with in calculus, there's logic behind them, there's reasoning behind them. Okay? And a lot of times there are shortcuts for very arduous processes. Okay? The quadratic, or sorry, completing the square could be a time-consuming process, where if we can abbreviate that process through this formula, it's very nice. Okay? Now there's some things about that formula that we want to be familiar with, and there are just some characteristics of it that's going to be very helpful for us in a lot of things that we do throughout the year. But first thing I want you guys to realize, regardless of what my quadratic equation looks like in regards to its variables, we got to pay attention to what this right here is. That's not what that variable is. That variable is an x, because that's the variable that we're using up there, correct? So if I had something like this, if I had, let's just go 3y squared minus 5y. There's an example on here, so I want to make sure that I do the same example. 3y squared minus 5y minus 1 equals 0. You see on the board that it's x's, right? I want to change the variable to make sure you guys understand. I have to pay attention to that because it tells me a lot of stuff with some of the things that we're going to do throughout the year. Quadratic formula is always, like I said, opposite b plus or minus b squared minus 4ac all over 2a. Okay? And it's always equal to something. Okay? Your formulas are going to be equations, right? They're not expressions, they're equations. So you got to have both sides. A lot of people neglect this side. But what is the variable that we're using? Yeah, that's y now. So y is equal to that. Okay? So we can go through, we can do that example. Okay, y is equal to the opposite of b would be positive 5. Plus or minus. Now b squared would be 25. Minus 4, a is 3, c is negative 1. All over 2a, which is 6, right? The number one place that people make mistakes is they lack the ability to evaluate that expression first, okay? And to do it accurately with the correct sign, okay? Make sure you know that order of operations tells us we have to do multiplication before we do any adding and subtracting, right? Okay? So we need to go, maybe you're a person that says, I'm going to do 3 times negative 1, so it gives you negative 3, right? But you still have 25 minus 4 times negative 3. So you still got to do that multiplication before you do any subtraction, right? So you need to do all of this first. And that's going to give you what? Positive 12? Does that make sense to everybody? I'm going to rewrite that as 5 plus or minus 25 plus 12 would be 37 all over 6. Remember that yields 2 solutions. 5 plus radical 37 over 6 and 5 minus radical 37 over 6. We would like to pay attention to that 37. That 37 tells us some nice information. We'll get into a little bit more detail here in a moment. But what kind of number is 37? It's prime. Okay? It's only divisible by 1 in itself, right? Okay? So 37 is prime, so this doesn't simplify any. That's my solution. Okay? Pay attention to how they want you to write your answers. Okay? They might say leave it in simplified radical form. They might say round to the hundredths place or thousandths place or something like that. So just be cautious of that. So that is what y is equal to. Is everybody okay with that? All right. at some point this year, we're going to get into this. And this is why I talk about this now, is that we'll eventually have 3y to the 4th. Just stay with me here. 5y squared minus 1 is equal to 0. Okay? Is that the exact same thing I started with, but I've squared the y's? That makes sense to everybody? So what I would do, and what I caution you to do, and I'm going to suggest that you do this, is I'm going to write this as 3y squared squared. That's still 3y to the 4th? Minus then, this kind of looks weird why I would do this, but you'll see it in a moment. Y squared to the 1st minus 1 is equal to 0. Now, what we see here is that this is in quadratic form. Exponent of 2, the next exponent is 1, the next exponent is 0, right? That's quadratic form. So now the variable, though, that I'm solving for, the variable is now y squared, correct? So when I come down here and I set the quadratic equation, the variable is y squared. So here, I have y squared is equal to that. Y squared is equal to that. How can I solve for y? Square root that thing, and now I've solved basically our first quartic equation. Okay? Does that kind of make sense? You always have to be leery of what variable is being used. Later down the road, we'll see something like this. 3 cosine squared x minus 5 cosine x plus minus 1 equals 0. Does that look very similar to what we started with? Y squared minus, or 3y squared minus 5y minus 1 equals 0. The only thing that's different is that expression there, right? So what we do when we solve the quadratic equation, it's cosine x is equal to opposite of b plus or minus all that garbage all over 2x. Does that make sense? Okay? So it's very, very, very important that we pay attention to what variable is being used. And a lot of people neglect that and they forget that when I have a formula is an equation. So you need both sides. Even if that one side is very basic, just one variable type thing like x, or if I'm doing area, area is equal to length times width. I need that a on the left-hand side. That's important to us. Okay. I'm going to leave these examples for you to kind of walk through. Throughout the PowerPoints, if there's a big blue rectangle, there's information behind that. Okay. So you need to delete those out, and it walks you through that first problem, and it's going to walk you through a couple others as well. Okay. I think that being something that we've talked about in the past and we've worked with in other classes, we can kind of do some hit and miss type stuff with it. Okay, I don't have to talk great detail about it. What's the word discriminant mean? Or what is maybe a root word that you see when you see the word discriminant? Discriminate? That make? Okay, now when you hear the word discriminate, a lot of us have like a negative connotation with the word discriminate, right? And it kind of makes, in social life it means we're picking out differences, right? And we're going to focus on those differences and make judgments about them, okay? But discriminate, just in everyday English, just means to recognize a difference. To see, how one thing is different from another, okay? And there's usually a characteristic that allows you to discriminate things, right? Okay? So, algebraically here, the discriminant is going to allow us to recognize the types of solutions that we have for a quadratic equation. Okay? Understand every quadratic equation graphically is going to be what type of shape? What's the largest exponent that we'll ever have in a quadratic equation? 2, right? So anything squared, algebraically, x squared, 2x squared, 3x squared, what are those? Parabolas. Okay? So a quadratic equation, if I draw my parabola, we start talking about the different ways that a parabola can look. Okay? I'm just going to draw them all concave up. Okay? But they could also be concave down here. We'll talk about the first one. It says if d is less than 0. Okay? D, capital D being the symbol that we use for discriminant. And they're saying that the b squared minus 4ac, the part underneath the radical, is that characteristic that's going to allow us to tell whether this function is different than another type of function. Okay? or this quadratic equation is different than this quadratic equation. So the b squared minus 4ac is that discriminating feature. All right? They're saying if that's negative, b is less than 0. That means negative numbers, right? So d is less than 0. Okay? What kind of numbers are you allowed to take square roots of? Positive or can you take square root of 0? Yeah. Is 0 positive? That's the question. A lot of times we refer to 0 as a non-negative number. Okay? We say it's not negative, but we're not going to say that it's positive as well. Does that kind of make sense? Okay. So d is less than 0. So negative numbers. You guys know you can't take square roots of negative numbers, right? So if I go through this and I find, b squared minus 4ac is like negative 10. Okay. So let's say just an example here. I have b squared minus 4ac, whatever those become, is negative 10. What did you guys learn last year that you rewrite that as? With that negative underneath the radical. I. Okay? So we got I radical 10, correct? Where do I graph that? On an x and y axis, can you graph I? No, can't graph imaginary numbers. Because that's a complex number. Okay? And this is the real plane, not the complex plane. So we can't graph R. Alright? But what that tells us graphically about our function, our quadratic equation, is that maybe it looks something like that. Okay? And we'll talk about some features here in a little bit that can compare the three different types of solutions that we can come up with. The next situation is when the discriminant is equal to 0. So my b squared and my 4ac are basically opposite to one another, right? Okay? Those go to 0. So you would see something like this. B squared minus 4ac. You do all your work, you get 0. Is there a number that when I multiply it by itself, I can get 0?
0.
0. Okay? So, the discriminant is 0, so that's good. That can happen. Alright? Now think about this. If my discriminant is 0, let's say I go to a quadratic equation where we had, the opposite of b plus or minus the discriminant all over 2a. If this thing is 0, it goes away, right? b plus 0 or b minus 0 is still just b, right? Or the opposite of b in this case. So now I just get x is equal to the opposite of b over 2a. How many solutions is that? It's just one, right? The plus or minus aspect has disappeared because of that 0. We're adding 0 over subtracting 0. Okay? So this meant, I will come back to writing how many solutions we get here. But this means when d is equal to 0, we have something like that. Okay? Where that curve is now just touching the x-axis. You guys remember what that word was for just touching the x-axis? Tangent. Okay? So now, we talked about negative numbers. We talked about 0. So now d has to be what? Greater than 0. Okay? And that's when you're going to get every component of this. Okay? Well, b could still be 0, but you'll get a plus or minus solution. Does that make sense? Okay? So you'll have some multiple solutions here. And the picture for that looks something like this. Or it could look something like that. Okay? So going back through here, d is less than 0. What that tells me is that there are no real solutions. No real solutions. Okay? Now, if there are no real solutions, it does tell me something about those non-real solutions that are going to incorporate I. It tells me I have 2 of those. Okay? But we can't graph it. Alright? If d is equal to 0, but discriminant is 0, that tells me I have 1 real solution. And If D is greater than 0, so we know what I have there? 2 real solutions. Okay? Now graphically, 0 x-intercepts, 1 x-intercept, 2 x-intercepts, right? That makes sense? So the discriminant allows me, the discriminant should be something we can calculate pretty quick. B squared minus 4ac. Everybody can do that multiplication, subtraction. We should be able to do that pretty quickly and understand before we do anything else, we now graphically understand how many times we cross the x-axis. That's going to be one of the huge topics throughout the entire course, is to understand, before I even get into doing a whole lot of algebra, what is kind of a rough image of my graph. Okay? So this slide kind of walks you through that stuff. We want to make sure that whenever we do a quadratic equation, quadratic formula, anything with quadratics, that the a coefficient is not 0. That's really the only requirement we need. Okay? If a becomes 0, then ax squared disappears, right? We're left with bx plus c, and it breaks down to a linear equation. It's pretty easy to solve. All right. So they asked us, can we go through and find out these things? Okay. So if we look at the first one, and I'm just going to kind of go through this quickly because there are some other things I want to talk about here. But we just do b squared, so 16, minus 4 times 1 times negative 1. Well, negative 4 times negative 1 is positive 4. So we get 16 plus 4, which is 20. 20 is a positive number, right? So now comparing, that's my discriminant, and that tells me then that you have 2 real solutions. D was greater than 0, 2 distinct real solutions. Okay? Distinct means different, right? Okay? Because here, we really do get 2 solutions here when D is equal to 0. Okay? If you remember back to Mrs. Cole's class, you talked about double roots, right? Or multiplicity of roots. We'll talk about that again in this class. But if you have D is equal to 0, you actually get a double root there. That is a visual of tangency, okay, at that root. Distinct meaning different. Okay, so you have 2 explicitly different solutions. If you do the others, okay, you walk through. Okay, negative 12 squared is 144, right? Okay, and then negative 4 times 4 times 9. 4 times 9 is 36. Double it, you get 72. Double that again, you get 144. So I got 144 minus 144 as this discriminant. That's what that product there is. That becomes 144 there. So 144 minus 144, it gives me 0, right? Gives me then 1 real solution, exactly 1 real solution. And then you see this last one, you get negative 4/3 underneath the radical. So you can't do that. That's violating our idea of radicals right now. So that's less than 0. So you have no solutions there. Okay. Have you guys seen that before? You guys talked about discriminants before? Okay, good. They're going to be pretty useful for us as we move on to other functions. All right. Everything that we do in this class, every time we learn some new type of equation, hopefully again this is not new, whenever we start talking about equations, we want to go back to the idea of recognizing and realizing that math is meant for us to, a lot of times, apply it somewhere. Okay? How can we use it as a society to benefit society? Okay? Now there are some things in math that is just like pure curiosity. Okay? There's a course in math called number theory. And there's a lot of things in number theory that are very, very useful in the real world. But a lot of times, we as humans are just curious about what is the largest prime number, or things like, do we ever run out of prime numbers? Okay? Does that kind of make sense? Okay. And they have supercomputers that are just trying to generate algorithms that will prove whether a very, 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 very large number, maybe millions and millions of digits, is prime or not. Okay. Then we start to think, okay, if that's the curiosity, at some point, maybe down the road, those things are useful in the real world. Because prime numbers are very useful in encryption. Okay, you guys know what encryption is with computers and stuff like that, bank accounts, that type of stuff. Without prime numbers, we really don't have the ability mathematically to encrypt websites and bank accounts and your online activity and stuff like that. But initially, prime numbers were just a curiosity of people, and they started to work with them, and they found eventually a purpose with it. Okay? Same thing here. A lot of times